Welcome. Before we begin tonight's workshop, I want to make a few announcements. Boston Data Festival kicks off at Nerd Center on 18 September. We now have a schedule that's up on our website, so if you want to know more about Boston Data Festival and all the events we have lined up, please visit our website. Then Open Data Science Conference San Francisco schedule is up on our website. Please visit opendatascicon.com, and registration is also open, so if you want to know more about the event, please visit that website. For Open Data Science, we're looking for bloggers, so if you're interested in blogging about data science, or if you know anyone who is interested in blogging, get in touch with Alicia or Tim there. Clap your hands. All right, great. That's our team. And Ty, who's Ty? Is that right? Ty?
Yeah.
He's one of our newest members. All right, great. So those are the announcements. Before I introduce Lukas, we just wanted to, on behalf of Open Data Science team, we just wanted to thank you for sponsoring our Open Data Science Conference San Francisco. Without your team, would not have been possible. So thank you. Really appreciate your help. As you already know from the meetup page, Lukas has an exemplary background. Lukas graduated from Stanford with a degree in mathematics and computer science. Before co-founding CrowdFlower, he worked as a senior scientist with the ranking and management team at PowerSet Inc. that was later acquired by Microsoft. Prior to that, he also held the search relevance team for Yahoo Japan. So thank you, Lukas, for agreeing to speak at our meetup. And
awesome. Thanks everyone for coming. Should we get started? So I'm feeling a little nervous, so I just want to get this out of the way. So y'all can leave now if you want. I'm definitely not an algorithms expert. I've written, published a handful of papers on machine learning, but at this point that was a long time ago. So I was looking at the people who signed up for the meetup, and I think there are a lot of people smarter than me about algorithms. I'm also not a Python expert. I spent most of my career where I was actually doing a lot of programming in R and C++. And I've never done a workshop before. So maybe you think of me more as a facilitator than a leader of this workshop. I do run a company called CrowdFlower. Has anyone used CrowdFlower? Yeah. Awesome. Well, so what CrowdFlower does, just briefly, is we help get labeled data for machine learning. So we end up working with a lot of machine learning teams. So I've watched a lot of machine learning get deployed into production, and so I'm really passionate about helping people do more machine learning. I think it's great. I think it's a useful thing that not enough companies do. And I think there's a lot of unnecessary kind of mystique around it. And I think I'm excited to help people try it that wouldn't otherwise already try machine learning. So I'll talk about my ideal audience for this. So one is that you've installed the Scikit Learn package, and I think you can't install it without Pandas and NumPy. How many folks have actually done that? Awesome. If you want to get your laptops to follow along, this is kind of designed for that. I've never actually tried to do this, so I'm not sure how it'll go, but it would be fun if you guys open up your laptop and follow along. And you can do that if you download my test data. So you can either get that from my bit.ly link, so it's bit.ly/crowdflower-data, or you can Google our CrowdFlower page, crowdflower.com/data for everyone, and then search on that page for the judge emotion about brands and products. Has anyone done that? Does anyone plan on doing that right now? Awesome, cool. And then finally, this is kind of designed for folks that don't know a lot about machine learning or haven't done it. Is anyone like that, or is everyone a machine learning expert? Anybody new to machine learning? Interesting. Okay. Does anyone fit this full description? Come in the front. Come on. This is designed for you in the back. Okay. So let's see how this goes. I will say if this gets boring, I have a couple options for you. So one I think would be cool is if you feel like this is too basic for you, and you have and you download the test data. We could run like a little mini Kaggle competition here, so you can model it the best or see kind of what techniques are effective. I'm kind of curious, right? Because we'll kind of go through learning this data set in kind of simple ways, but it'd be interesting to see if a bunch of people try modeling it in other ways, like kind of how effective that is. The other thing is, it might be nice if you, if you're sitting next to someone who's actually working, who has a laptop, but it might be nice if you help them work on this. And then finally, I won't get at all offended if you leave or want to go in the back and chat. I realize the meetup is kind of also for hanging out with people, so feel free to get up and walk around or move to the back. All right, so does anyone plan on following along with? Yeah. Question?
Just for people that already downloaded the data from HubSpot, what you have up here is the same.
Same data, yeah, that's right. Yep, yeah. Okay. Has anyone who's downloaded the data now?
Yeah.
Yeah? Any possible download these links, right? Yeah, they're good? Okay. Cool. Okay, so I'll tell you, I used R for most of my career. I think I'm probably more advanced on R than Python, but I really love Scikit Learn. I mean, I'm not a contributor, I'm not like a super user of it, but I think Scikit Learn is a really amazing framework for people that actually want to use machine learning in production and don't have a deep statistical background. So R, I think, is really designed for statisticians, whereas Scikit-Learn feels to me like it's really designed for engineers. And I really love that. So especially for folks that are kind of more engineering bent, I want to give you guys a chance to just step through how you actually build a real machine learning classifier. And then I also kind of want to give you a framework for kind of understanding the vocabulary of Scikit-Learn. Because I think an issue that I've seen, at least folks at my team run into when they start doing machine learning projects for the first time, is the language is really opaque for people that don't have a deep background in machine learning. But I think it's unnecessarily opaque. And so finally, you can follow along if you go to this GitHub. So I actually was kind of hoping that people would actually like follow these examples and we can like run these demos together and type the stuff in. This seems like the best way, to learn by doing. But I put all the stuff that I did up here so you can, if you get behind or ahead, you can pull out my examples. And also folks who are maybe more advanced can look at the examples and see if this is going to be relevant for them at all. Cool. Are people able to load this page? Has anyone loaded it? Yep. Cool. And if anybody wants to complain about my code or submit pull requests, I will appreciate it. My team does not let me commit code into CrowdFlower anymore, so don't worry if you're a CrowdFlower customer. And we use Ruby mostly anyway. Okay. So, man, this is going to be so basic for most of you. I apologize in advance. But so this is kind of this is sort of like how I think my parents view AI as like this kind of magical thing. And my teacher, Chris Manning, always uses this awesome picture of a baby with headphones, right? Where it's kind of like, babies, they're so magic, right? They learn things. And so we have this framework around AI and machine learning that it's like, it's somehow magic and somehow opaque. But I think when you do machine learning in the real world, it's a lot simpler and it's accessible. And I think the simpler way that I think about it, or that my professor talked about it, is kind of more like a classroom, right? So it's like you're going to feed an algorithm a whole bunch of examples, and it's going to generalize from them. And kind of the most like super simplest way to think about it is regression, right? So that's kind of that. I think there's a spectrum from regression to machine learning, and this is kind of the simplest way to think about it. So here we have lean body mass and muscle strength, and if you get a lean body mass number, you try to predict the muscle strength from that. And linear regression is a great way to do it in this case. And just because there's one variable doesn't mean that it's necessarily going to be simple, right? So if you're trying to predict the weather, right, you can see it's a much more complicated function. And so how did you predict that? It's kind of an interesting question to think about. So here we have the weather over time and the temperature, and you can imagine essentially a well-formed problem is kind of what's the weather going to be the next time interval, and kind of doing some kind of modeling of that slope is I think essentially a kind of machine learning. My brother-in-law is a stats professor, and I'm like imagining him complaining about this in my in my head. He often says, like machine learning people just take stuff from stats and kind of call it machine learning and do things improperly. But just from like a hand-wavy perspective, I think that this is totally machine learning project, and Scikit Learn actually totally could do this. But then I think where it gets more interesting and kind of Scikit Learn gets more relevant is when you start to get into multivariable regression, right? So this is real data from Scikit Learn, and you can think of it as just a spreadsheet. And so you have a whole bunch of numbers, right? From a whole set of numbers or a matrix, mathematicians would call it, or computer scientists, what do we call it? Like an array of arrays, right? You try to predict some kind of value. This is multivariable regression, and then machine learning might be the case where instead of, or the case that it covers, right, is instead of like numbers of these things, like you have more complicated things. These things like social network or images or text. And so what we're going to try to do today is automate a data set that I collected, which is judge emotions about brands and products. So I can show you. I can show you exactly how it looks. So this is, so what my company does is collects this data, and you can use our tool for free actually if you make the data open and available. So that's how we got that data for everyone library. So, and then I can use it for things like this. And you can use it for training data, testing your machine learning algorithms. But so this is, I'll just show you exactly how it's collected, right? So here we have a company that's interested in brands and products and the sentiment around that, right? So here's a tweet. I just noticed DST is coming this weekend. How many iPhone users will be an hour late at South by Southwest on Sunday morning, right? So this probably has no emotion towards a brand or product. Let's see if there's one that does, right? So here we go, best. First in line for iPad 2 at South by Southwest pop-up. So you might say there's positive emotion here. Maybe it's towards the iPad. But again, you sort of see, it's not totally clear if this is towards the iPad. It sort of shows this is a little bit of a complicated thing requiring some judgment. But this is a really common, machine learning application. It's a common thing that our customers want to do with human beings. Does this make sense? People understand this? Yep. And so, the data that comes back, looks like this. Actually, I'll open it in Excel so it's probably more clear. So this should be the data that you downloaded. So it has 3 columns, right? There's the tweet text, there's the emotion the tweet directed at, right? So that's the product, and is the emotion directed at a brand or product, right? So that's going to be like negative or positive, or no emotion, or I can't tell. How many people have this data with them? Awesome, cool, okay. So we can really do this. All right. So the first thing is to load the data, right? So this is super basic. And so I made I was kind of like working on the data and then saving it as I went along. So this would be the load_data.py in the GitHub repository. But we can walk through exactly what this is doing. And I think it would be cool to really type this in and see it if you haven't actually built a classifier before. We're going to do it. Yeah.
Could you make it text larger?
Totally. Anybody know how to do that now? View.
Where'd you get that?
Response settings. Is that good? Yeah. Awesome. All right.
Where? Do you see the?
Okay. So just to give, how many people use data frames in Python? Cool. Okay. So I really like data frames. They kind of give you some of the awesome things about R. In Python, they're super helpful for exploring data. You can think of them as simply as like arrays that can do a bunch more things that are super useful. So you can actually follow along this whole. I think you can follow along this whole thing using arrays. I was kind of thinking that might make it a little more accessible to use arrays, except data frames are so awesome that if you do any machine learning, you should totally use them. So I'd introduce them as something you should try. So here I'm reading in the CSV, and then I'm calling target the column that's the is there a motion directed at a brand or product, and I'm calling the text the tweet text. So we're going to try to take this text and then predict the target. So here I'm printing out the first 5 rows of the target and the first 5 rows of the text. And so we can just run that. I should make this bigger too then. As you can see that the target data looks like these stacks of negative emotion and positive emotion. And then the actual text of the tweets looks like I have a 3G iPhone, etc. Cool. Okay. So now, Scikit Learn and most of machine learning really wants to work with matrices or arrays of numbers only. So we need a way to turn this this text into an array of numbers to work with it. This actually, I think in my view, this is the most important. This is the most important step actually when you do machine learning. Except maybe the data collection, since I work at the actual human data collection. But this is super important. So I stole this from another website, but what we're going to do first is something called bag of words. How many people know bag of words? Okay. How many people don't know bag of words? Am I teaching anyone? Awesome. Okay, cool. Excellent. So the way this is going to work is we're going to take literally each word, and we're going to count how many times it occurs in the tweet. Right, so we're gonna make. You can think of like a giant spreadsheet, right, where like each column is like a word. So it goes like A and aardvark, and we're gonna count how many times aardvark occurred in the tweet and how many times each thing occurred in the tweet. So most of these are gonna be zeros, right? So we're gonna want. Luckily, we're using something that kind of handles the sparse matrix in a cool way, so it's gonna account for the fact that most of these records are zeros. And that's how we're going to turn the text. That's the first way we're going to turn the text into numbers so that we can use normal regressions and machine learning algorithms. And so this process is called feature extraction, right? Basically turning your data into a matrix so that you can use algorithms on it. And so I have a thing called feature extraction.py. And so basically, I've taken the first part that I had in that loads the text here, right? So we get target and text, and then I import a thing called count vectorize from Scikit Learn. So Scikit Learn actually has a bunch of awesome options for doing this. So if you're more familiar with bag of words and you know about like TF-IDF, there's a great way to do that. There's a great way to do a hashing vectorizer that'll be faster. Right, so for people that are more advanced, there's a whole bunch of options. But the simplest thing, the thing that I just described of just putting the counts in, count vectorizer is a great way to do that. And so what we do here is we say, okay, we're going to do count vect equals count vectorizer. So that's going to initialize it. And we could put options here. And then we're going to fit the text. So what that's going to do is it's going to look through it, it's going to look at all the words in the text and make a dictionary, and then get ready to make that spreadsheet or that matrix of the counts of each word. So it'll say, oh, I see aardvark. Okay, that's going to be one word. Oh, I see iPad 3G. Yeah.
If I have a lot of errors, what does that mean?
Oh, it means, yeah, so I left an error in here because I wanted to show you what I spend most of my day doing, which is dealing with these crazy errors. And if any of you guys work on Scikit Learn, I recommend you make these errors a little more clear. It would definitely make it more accessible. So yeah, so I left an error in here. It's actually not an error in my code, it's an error in the data. Does anyone know why this error? Can anyone debug this? I'm curious. Yeah. Yeah, totally, yeah. You just know, I love it. Just sitting there, awesome. Yeah, what is it?
The debug?
Yeah.
The solution? Or?
Yeah, what's the solution?
Oh, you should probably need a new filter to filter the data from like whatever you use for empty features to np.nan.
Yeah, there's a missing record in record number 7, I think. So the text is just blank. This is like most of my life when I'm working on machine learning. Probably others of you that will know my pain here. So actually, we could change this here to do if we just fit the text from like 0 to 6. And this is like literally, this is how I debug this. This isn't, I didn't like put this in for effect. I got this error and I decided to leave it in to just kind of show my plate. So I thought, like, okay, I wonder if this runs on a subset of my data. And then it did. And then I noticed that it was that 7th record that was causing problems. And then I went into the spreadsheet and I was like, it's empty. So,
How do you get 7?
what's that?
How do you know that was number 7?
Oh, because I could literally open up the spreadsheet and I was like, like that's blank. Record number 7. And like probably like, there's like gonna be like Unicode errors and there's gonna be like all kinds of crazy problems because we actually do it. So I'm just showing you, because I really want you to become machine learning people that can build these things. You will encounter more of these. Okay, so I made a version that is a little more bulletproof. Which is called, so I made fixed text and fixed target. This is, let's follow along here. Feature extraction 2. So you can get that up the GitHub. And all I added here is these 2 lines. So this is, if you guys know data frame, you'll recognize this, but I'll just explain it for the folks that don't. So, basically I'm saying index on the text where it's not null. So basically take the text, only the chunk of text that's not null, which is basically all the rows of text except the 7th row. And then also for the target, remove the 7th row, the ones where it's not null. So now, you can see that it actually ran. And what it's doing is it's printing, so count_vect is that vectorizer. And so the vocabulary underscore is the list of vocabulary. So it's basically saying the index of each word. So I'm wondering, like, where's 3G? Is that in the vocabulary? And it turns out that it's number 168. And so you can modify the code. So you could say, it's another word that might be likely to be in there. We could say, like, apple. Where's that? So that's number 657. And you could say, well, okay, where's apple with a capital letter? And you can see, so it says none, right? So it's actually just lowercase in all the letters, which is kind of interesting, right? And you actually, if you type in, you look for like I, using that's missing. So that's interesting. So it's doing some filtering of words. But if you put in a lot of normal words, if you look at, if you go through this something you say, like, okay, South by Southwest is in there. I wonder if it removes the hashtag. Let's see. So South by Southwest is in there. Anyone?
Does that mean hashtag?
What's that?
What are the SXs that mean?
Oh, it's just the word. It's South by Southwest. It's in the. I was looking in this Excel for just words that show up. Yeah. I don't know if it was, but you could try it with a hashtag. That'd be a fun experiment. Because it's not in there. Cool. All right. So, so now we actually want to use this, right? So we have kind of this thing that's transforming the text into numbers, and we can, if you go to feature extraction _3, you can see here that I built the count vectorizer, fixed the text, and now I'm printing the transform of I love my iPhone. So the fit, you can see countVec.fit here sets everything up so it can run, right? So it's figuring out, okay, what's my dictionary of words, like what words map to what places in my matrix. And then the transform is actually going to turn this into a set of numbers. So, so if you run feature extraction 3, you can see that there's 3 numbers here. So 4, 5, 7, 3 might correspond to love or my or iPhone, right? So it's saying there's one kind of each. In fact, we could try, we can figure out which is it, because I love my iPhone. So 5169 must be the index of love. So this notation here, this kind of 0, 4, 5, 7, 3, it's basically indexes into the sparse array. So now it's kind of in a format where it's numerical, and it's ready to actually to run, right? So I mean, just a couple things to note, right? So one thing is the order is totally lost, right? So if I type my love iPhone, I'll actually get the same output, right? So it's totally ignoring the order, right? So the machine learning can never recover that information. And it's also omitting the I, which is kind of an interesting thing, right? So there's only 3 numbers here because it actually skips. Turns out that by default, Scikit Learn will skip single letter words in its kind of algorithm that does this. It's trying to help you. Anybody still with me? Anybody able to run them? Yeah? Cool. All right. So just want to comment, we've actually made a whole bunch of important choices. I think we've actually already kind of made the most important choices in doing this, right? So if you actually look at the feature, the count vectorizer class, it has all these kind of scary parameters. And you don't have to worry about these parameters. I think you can use the defaults and it'll often work for you, especially in English. But I want to kind of help you understand what these parameters are, because if you're going to monkey with any of the default settings of Scikit-Learn, this is what I would suggest monkeying with. So should we remove rare words? It's kind of an interesting question, right? So if the word only shows up once in my my text ever, like there might be a typo, it might not really matter. In fact, how can you really learn from just one example? So there's an option to remove rare words you can use, which is the min-df, right? Which means the minimum document frequency. And actually, by default, it's 1. So I don't know. Does that remove words that recur once then? I'm not sure if it's like greater than or equal to, or I'm not sure if words occurring once get removed by that or not. You can experiment. Also, you might want to remove common words, right? So it actually has the default setting here is 1.0. So this is a little bit confusing, right? But if you put in a real number between 0 and 1, like a decimal number, it'll remove that. So if I have 0.9 for max df, it'll remove any word that occurs in 9% of the cases, right? So like the might occur so much that it's just like not that interesting for my algorithm. It also removes what they call stop words. So it has a list of English stop words. Oh, no, it doesn't. So actually, by default, stop words is none. So, but you could say, I have a bunch of words that I know have kind of no semantic meaning, like is and. And so you can say, okay, just ignore those words because they're not going to help me at all. It actually lowercases all the words, which is an interesting choice. So lowercase is true. And then finally, I think the most interesting thing is actually what is a word, right? It's actually more complicated than you think. So in many Asian languages, right, they actually don't put spaces between words. This is something I worked on at Stanford, so I know a lot about it. But even in English, right, and especially with tweets, it's pretty confusing, right? So it's like this hashtag South by Southwest. We removed the hashtag. Like, does a hashtag have any extra meaning? I think, like 100% is like a little different than 100 probably. But, should you maybe keep the percent? This 5,000 dash square dash foot, should that be like treated as one thing or multiple things? This is actually, I would say this tokenization is a really important step. And I would say the thing that I found, the first thing I kind of look for when I do many natural language processing tasks with machine learning is I think a lot about this kind of tokenization. And what's cool about this is you don't have to be like a genius to improve this. You can actually kind of use some common sense of like what would help this algorithm in this case, right? Like I think with tweets, preserving the hashtag is probably really important, right? So you can actually look at the tokenization algorithm here. It's a regex, right? So this is the default Scikit Learn tokenization pattern, which is saying, a word character followed by another, at least one more word character, then a break. I recommend if you change one thing, one default, I would change this. Because, for example, it's throwing out exclamation points, right? Like the exclamation marks are going to be really helpful probably for sentiment, right? I mean, how many exclamation points there are in the tweet, I bet you that contains some information. But let's not do that yet. So I kind of want to just like walk through like getting to the end, and then we can go back and kind of refine. But if anybody is bored and feels like they're more advanced than I'm talking, then maybe see if you can find a better tokenization pattern and tell us. That would be cool. Okay, so now we need to choose an algorithm, right? So there's tons and tons of algorithms, and this is what lots of researchers work on to pick what to do once you have a matrix and you want to go from that numerical matrix to some objective function, right? So this is a very well-posed problem that's like deeply studied, and unfortunately it's studied by lots of different people that name their algorithms all kinds of weird things, right? So, there's like neural nets, which is almost like too awesome of a name, like it sounds so cool. But like a lot of people are like, oh, like I should use a neural net. And then there's names like support vector machine, which sound like, I think like intimidating, and these like are really not descriptive, right? But there's this cool, the Scikit Learn team made a cool flowchart for picking, which I like want to quibble with because I work on this stuff and I care about this stuff, but I think it's good enough. So, once you have your data in a matrix, you can actually look at this flowchart so we can follow it. So it starts off, it says, okay, how many samples of data do I have? So I have greater than 50 samples.
Sorry, could you maximize that?
Oh, yeah, sorry. I also have a link if you want to. Yes.
Yeah.
Okay, cool. So I bet you could Google Scikit Learn and choose an algorithm, you'll also find this. But let's follow. So it says, okay, greater than 50 examples. I kind of love this, right? So if it's no, then it's like, don't even try. Go get more data. I kind of agree with this. There actually is some interesting cases in like bioinformatics stuff, which is really expensive to get a row. That there is some interesting research on this, but luckily we don't have to deal with that. So are we predicting a category? Actually, this is kind of arguable in this case, right? Because we have positive sentiment and negative sentiment and neutral. So you could say, okay, that's like a range of things. Like there's like, maybe you could say like negative is like -1 and positive should be +1, neutral is 0, and it's sort of like predicting something on a spectrum. But I'm just going to say we are predicting a category here. So there's sort of like 3 categories. There's like neutral, positive, and negative. And I think that's a fine way to look at it. So we're going to say yes. And then we're going to say, okay, do we have labeled data? And yes, thank God we do, because that's going to make the algorithm a lot better and everything a lot easier. I would say every successful, almost every successful deployment of machine learning in the real world I've worked on has had labeled data. So now we're in the realm of classifications. We're in this upper left field. And so it says, okay, do we have less than 100,000 samples? And we do actually in this case. So I think it's about 10,000 samples. So it suggests linear SVC, which is SVM, if you know that. I actually tried the Scikit Learn linear SVC on this data, and it was actually kind of weird for me. And so that made me think, okay, this is like pretty hard to get right. And I actually kind of liked the way they say, okay, not working. So it didn't work for me for some reason. And also, like, personally, I wouldn't start with an SVM for this, but you could. But so it says, okay, that's not working. In my case, it's true. But if anybody wants to try to get it working, another interesting project for advanced listeners, go to text data. We do have text data. So it started out as text data. Now it's numbers. But so then if that's yes, then it suggests naive Bayes, which is a really easy, fast algorithm. You know, kind of never the best, but always pretty good. And so that's the one that we'll go with.
So even though your data is numbers, you're running with the Bayes?
Yeah, so it's a little confusing the way it says text data. And the thing is, it's always going to be numbers once you get to this, but it's like, it's just abbreviated. Basically, you just start with text data. Because the text data is a little unusual that it's like super sparse. So like our numbers are mostly zeros in our giant matrix. So naive Bayes will handle that super well. So let's do it. So one thing that'll happen with any of these end nodes is, you know, you say naive Bayes, and then you Google Scikit Learn naive Bayes. There's actually, there's like multinomial naive Bayes and Gaussian naive Bayes and Bernoulli naive Bayes. And I think there was a time when I knew the difference, but to be honest, I didn't know the difference. So I actually think all of them will work fine in this case, but they kind of explain it, like slightly different. They handle the multi-class situation a little bit differently. Sorry to my brother-in-law, I'm coaching this. So let's see. So I call that classifier. So, you know, starts off the same. We do the vectorization. We fit the vectorizer, right? So that like learns what the vectorizer is going to do. Then we transform it. So now we have the fixed text into counts. So counts is our big matrix in classifier UI. Now we import multinomial naive Bayes, multinomial NB. And so then we do, we initialize it. We basically take all the defaults here. And then we fit the counts and against our target. So the fixed target is our fixed target data. And then we do a prediction on I love my iPhone. And we had to do we had to transform that data with the count vectorizer to turn that I love my iPhone sentence into the kind of ones and zeros that the naive Bayes classifier will understand. So let's run that. Classifier.py. Positive motion. So it worked. Anyone else get it to work? Anyone follow along? Yeah, awesome. So you can try, and this is kind of fun, so you can try some other stuff. So iPhone costs too much. Negative emotion. Seems like it's plausibly working. I mean, one thing to note, right? Remember, we threw away any kind of information, so we say cost iPhone much too. You can be sure that it will return the same thing, even though it's sort of nonsense. And great, and this is great. You can really like now deploy this and use this, right? So if you wanted to use sentiment, now you have a thing that seems to plausibly predict sentiment. So you know, at this point, you actually you have a working thing, and maybe you can use this for something at your work. But let's keep going. So okay, one thing I want to say, there's a bunch of scary choices, right? So naive Bayes actually, I kind of like naive Bayes because it doesn't have a lot of parameters. Well, first of all, you're picking multinomial naive Bayes or Gaussian naive Bayes versus Bernoulli naive Bayes, and then there's always a bunch of parameters that are Greek letters. So there's going to be like an alpha, and if you use a more advanced algorithm, there's going to be like a bunch of other Greek letters. And I think Scikit Learn mostly does a good job of reasonable defaults. And you can always try different numbers, but I think like mostly I would just say don't be scared. Like use the defaults and see if it works for you. I think that this is a lot less important to modify typically than the previous step. You can also try other algorithms. I don't necessarily think this is usually the best use of your time, in my opinion. Even though I worked on this stuff. I mean, I think like a lot of people, they love this stuff. They love making algorithms. That's kind of why we have so many algorithms in my view. But often the results of changing this is I'll kind of show you how to change this more efficiently later on. But let's keep going. So now, okay, we want to know how. We want to know, okay, this seems to work for like 1 or 2 examples, but we want to see how well is this algorithm actually working. So I have test algorithm 1.py, so we basically do the same thing. And now we get to the end and we say, okay, we're going to predict on the counts, right? So remember, the counts is the big array that we created from the text data. So we're basically going to predict on all that data that we had and see how well it works. Sorry, so then we're going to use, we're going to basically say how often the predictions equal the fixed target, which that would be like positive motion or negative motion. So basically say how many times do the predictions actually match the fixed target. So 7,229 out of, I think it's around 9,000 records in the that we have, right? So it seems to be predicting about like 75% of the time, but most of you are probably thinking this is a bad idea, right? Because we're actually testing out the same data that it learned from, which is not going to really happen in the real world, right? So in the real world, it's going to see new things that it hadn't actually seen before, right? So we need some way to kind of simulate what's it like for this algorithm to encounter new stuff. And I think Scikit Learn makes this awesomely easy to do. Does that make sense? The idea is that we want to. So first of all, simplest thing that you can do is you can basically do test train split. So you can train it on 70% of your data and test it on 30%. So if you go to test algorithm 2, I basically fit the data on the first 6,000 rows. And then I test it on the last 3,000. So we can see if that actually gets worse. As you can see, that it actually does get worse, right? So it goes from like 75% accurate on when it's testing on itself to kind of 60% accurate when it's testing on data that wasn't trained on. So when we train only on the first 6,000 rows and test on the last 3,000, as you kind of expect, the algorithm gets a little worse. But this is kind of more like real life, right? Because in real life, the tweets that you're going to have a classifier are probably not the tweets that you showed when it's training.
Since you have the data yourself, like, are you able to like check to see whether or not you're actually going correctly? Like, should it be 75%, or should you be expect like actually it should be more like 90% correct with your own data set? Yeah, so that's what I'm trying to do here. So the first thing I did, where it was like 75%, was I basically just tested it on its own data that it was trained on. But the second thing I did was I held out a set of a third of the data and basically said, okay, we're going to test it on that. We're going to train it only on some of the data. Yeah, because we're going to basically do this fit here on only here.
You have a question on the statement, like.
What's that?
What we have, you have a question, like, does it cost too much?
Sorry?
If you have a question on the statement.
A question?
Yes. Like, does it cost too much? Is it negative or does it too much?
I'm not sure it's all.
It's just sort of asking.
Oh, what's the center of asking for? Oh, what would it be labeled as?
Yes.
It sort of depends on the instructions, right? So we have to kind of go back to like how it was labeled, right? So we can look at and this is why I show you the actual job, where it kind of directs you. But it's a little vague, right? So actually, I think some of the errors that it's making, so it's matching 60% of the time. But I think a lot of the mistakes are probably these vague cases. So you can actually go through each record and look at, where it's getting things right and where it's getting things wrong. And then another thing that people never do enough of is based. Yeah, sorry.
Sorry, is there an error in this? There's the line fixed target equals target, qb.all. Shouldn't that be target text? No. No, okay, never mind, sorry.
No, it's awesome. I'm glad you're following along. So one thing to think about is like, okay, is that 60% accuracy good or bad, right? And one way to think about it is, okay, there's kind of 4 categories here. So if it was picking randomly from the categories, it would be 25% accurate. So if it was below 25% accurate, I think we would say, man, this algorithm is horrible, right? It's like worse than random, right? But actually, a lot of times I think people don't think about these baselines, and they'll give you an algorithm that has accuracy worse than random. I actually remember running a machine learning contest, or even if you guys have entered Kaggle contests, they'll often have a baseline that's like picking randomly, and you'll see people sometimes submit an algorithm that's like worse than random, and you kind of wonder, what's happening there. Like, and so I think the first thing to think of is kind of what are the baselines. Scikit Learn is really good at helping you make these baselines. So they have a thing that it's like one of the awesome things about this tool is that you can set up a dummy classifier. So in this case, we'll have the dummy classifier guess the most common thing, right? Because the data is kind of uneven. So I think the most common thing is that there's no sentiment in the data. So it'd be interesting to see if 60% is really how often that happens, right? Because if it's really just, maybe it's just like, if it's just as good as picking the most common thing, then we're not really learning anything here. So I have test algorithm underscore dummy, where you can see I've replaced the NB classifier with this thing called dummy classifier. And I've said, okay, my dummy classifier strategy is going to be most frequent. And you can see it's a little less, right? So I think we could say that algorithm is doing something, but maybe it's not awesome yet. So did that make sense? Yeah.
Is there an easy way to see precision and recall right now? Is that built in?
I'm not sure. What is it called? Yeah, score. Yeah. I'm not. Yeah, I guess I feel like for this, probably the right measure of accuracy is actually accuracy. For guessing positive or negative. But that's maybe debatable. But I'm just saying, like the thing we're trying to optimize is the amount of matching, not precision recall in this case. Okay, so let's keep going. So really the best way to maybe, or another good way to guess the accuracy is to do cross-validation, right? So that's where we're gonna train it on 90% of the data and test it on 10% of the data, but we're gonna use each possible 10%, right? So we'll divide it into 10 chunks, and we'll train on 9 of the chunks and test on one of the other chunks, and then we can actually look at how well it does on each chunk, and not only tell us kind of in essence the accuracy, but we can also see how much variance there is, right? Because we can see kind of how each chunk changes. And I'll say an important thing here is actually how we're ordering the data, right? Because if the order of the data that I have is actually not random, there's actually duplicates in order. So if you think about that, if I randomly select my chunks, it might do better because it might get a duplicate in the training and the test. And that might be too. But so actually I have that here. So you have test algorithm cross-validation, which you can run. All right, let me show you what it does. So again, this is super simple, right? So you import cross-validation. Obviously, this scores equals cross-validation. Here I'm putting in my algorithm, the counts, which is the input data, the target, and then the number of chunks that I want it to divide into. And so what that'll do is it'll show 10 different scores. So I can see kind of the range of accuracy that I'm likely to get on chunks of data, right? So it looks like I'm getting between 62% accuracy and 68% accuracy, with the average being around 65% accuracy. And then we can try with the dummy, right? So then this is going to be easy for us to do, right? So we basically just change our just replace NB classifier with dummy classifier here and run it. So you can see it's pretty similar to when we trained on 70% and tested on 30%. So the dummy classifier is around 60%, and the our advanced naive-based classifier is around 65%. So we could spin that as like a 8% error reduction, I guess, 9%. All right, let's keep going. So pipeline. So now we're starting to get into like why. I mean, this is something that you really don't have in R easily, but makes your life a lot easier in Scikit Learn. So you see, actually, our classifier kind of has 2 steps right now, right? So there's a step that kind of transforms your text into numbers, and then a step that predicts your numbers to the outcome that you want. So if we combine those 2 steps, we can it'll make our lives a lot easier. And you can see that we're going to add some more steps. So this metaphor is going to work even better. So basically here we say, so in the past I was saying, okay, first transform the data into counts, and then predict off the counts. Here I basically set up a pipeline where I say the first step is the count vectorizer, and the second step is the multinomial naive Bayes, right? And so I'll call that pipeline P, and now I can just call P.fit. Right, and that sets everything up. Right, it sets up the counts, and it sets up the multinomial naive Bayes, and then I can just call predict on that pipeline. So this should be the exact same thing, but just a little more succinctly as the first time we ran the classifier. So hopefully, I think we tried it on our my iPhone was positive. So let's just check with the python.py that we actually get the same result again. And so we get positive most points. That's good. So it seems to be working. But then we can do a lot more with this. So, so one thing that we might want to do is we might want to actually look at not just the individual words, but the pairs of words, right? So, O grade has kind of a different connotation than grade. Right? So our system has no chance of understanding the sarcasm in O grade right now because we're just showing it the counts of each individual word. The order is completely lost. But actually, it's often powerful to show it the pairs of words and actually do the counts of the pairs of words. Right now, this is going to be like this is going to be a big matrix that we're talking about. So let's do it. So pipeline diagrams.py shows you how easy it is to do. So we basically it's an option in count vectorizer. So we say the n-gram range is 1, 2, so we're going to show up the individual words and then pairs of words. And then I have a little bit of craziness down here. So basically, this name steps basically gets a dictionary of all the steps, which is why I've actually named the steps in the pipeline. So I'm pulling out the count vectorizer step, and then looking at the vocabulary that I did before, and I'm basically going to look at does garage sale show up? Because I saw that in the data. Right, so this is what I did to test. It's actually getting the pairs of words. So let's see if that works. So you can see the garage sale shows up as word number 18967. And actually, I looked at the length of all the name steps and all the vocabulary and count. So this is like all the pairs that there are is 59,614 pairs of words and individual words. So this is off of 10,000 rows of input data. Right, but you can see how this starts to get big really fast. But this actually just worked right now, right? So my little laptop was fine with this so far. But we may run into trouble down the road looking at all the pairs. But let's actually see how well it works. So I have pipeline bigrams accuracy where I added, okay, let's check the score and the mean score, right? So we're going to do the cross-validation on the multinomial naive Bayes. Anyone still following along? Yeah, awesome. So you can see it's taking a little longer because it's got all the pairs in there. It actually has to do 10 times, remember, for each step in the cross-validation. And you can see, look at that, it's a 68% accuracy. right? So actually the pairs of words probably added a little bit. So you can see it's ranging here from kind of 64% accurate to 68. And now if we go up, when we were just doing the cross-validation on the simple one with the individual words, it was kind of ranging from 62 to 70. So that feels like a significant improvement. It feels like maybe it's not noise. Although you can see it's a little debatable, right? On some of the segments, it's actually a little bit worse. So, you know, we could probably do some math to figure it out, but I think most people just eyeball it like this. But then, you know, the thing about using these pairs is you're gonna actually start to like run out of memory in your computer pretty fast, right? So if we expand it to like 100,000 rows, there's gonna be so many pairs that I think my computer's gonna get slower and slower and slower. It's just not gonna scale. So that's why you might want to put a step called feature selection, right? So a lot of algorithms want a feature selection step, and actually Scikit Learn has a whole bunch of different options for feature selection. I'm gonna use a really simple, quick one. That's basically going to look at how correlated each individual feature is with the outcome and pick the best one. But there's a bunch of different ways to do it. But if you look at feature selection.py, you can see that now my pipeline has 3 steps, right? So the first step is taking this list of text and turning it into a matrix of ones and zeros typically, or numbers and zeros. Then my second step is actually going to shrink the matrix. Based on this select k-best algorithm, this music chi-squared test. And I'm gonna pick the top 10,000 features here, and then it's gonna do the multinomial regression. And then I'm just gonna do the cross-validation. So I'm gonna just add this little step, and I'm gonna see how well it works, and hopefully it'll run a little faster than the last time. So feature selection.
Question?
Yeah.
So you're doing bigrams and single words together. Worst to pull out the single words and just do bigrams?
I think we could try that. Actually, I think if we do this, if we change the 2 and 2, we'll only have the pairs. But you know, it might be better to use the individual words because the individual words might be more predictive, typically, right? Like if I say great, kind of doesn't matter. Well, actually, great has the O grade thing I was talking about. But if I say like awesome, it might be the case that that's always correlated with better sentiment. So I might actually want to have that in there. But we could try. We could totally just try it right now. So we'll change it to 2. So you can see you got 66% accuracy with the individual words and the pairs. I also noticed that this seems a little bit lower than the 68%. Although again, this is kind of within the noise, right? If you look at each time it ran, but it looks like maybe the feature selection is hurting the accuracy a little bit because it's throwing out some information. Although maybe it's noise. But let's run it again. So this is just going to be the pairs of words, like you suggested. And so it looks like it's about the same with the pairs with the individual ones. So yeah, you could just do the pairs. But that's not going to decrease the amount very much because there's so many more pairs than individual words.
Is it pairs next to adjacent?
Adjacent pairs, yeah. Yeah, exactly. Yeah, I guess if it was all the pairs, then there isn't really any. Well, is there information? For some algorithms that would help it, and I think some algorithms would. Like naive Bayes, it actually would probably change things to show every pair. But that would be a really unusual approach, I think. So now it's like we've kind of looked at a whole bunch of different, I think one of the things that's intimidating about machine learning for folks is the amount of different parameters. Actually, one really powerful thing that I used to do this by hand a lot, but Scikit Learn makes this like super easy, right? So you can actually just do what they call grid search, which is basically like, let's just like try everything and see what gets the highest accuracy, right? So we can say, hey, that alpha parameter with value base, I mean, I think there was a time when I knew what that was, and I kind of give you a handwave explanation. But to be honest, like, I really have no idea what that does. But I can kind of throw in, like, maybe say it's like 10 to the -2, 10 to the -3, 10 to the -4. Let's kind of see what's the best value for that parameter. We'll just try them all. And then, like we're saying, this remember that max document frequency thing we were talking about? I don't really know if that's going to help. It doesn't seem like a word that shows up in every single piece of text would help very much, but let's try printing it out. Maybe that'll be good. And then, like rare words, should we throw them out? Like, let's just try throwing out some of the rare words, and let's try using the pairs of n-grams and the individual n-grams, right? So grid search.py does that, and you'll see like how easy it was to add this, right? So there's like this convention here, right, where I say the name of the pipeline step __, and then the attribute that accepted, and I just give it the parameters that I would want to try with it. And so I'm going to try all these, and then you can see I had here I was trying feature selection, but I'll take that out for time. You could add it back in if you want, and see how that works for you. And then this grid search is basically going to take my dictionary of parameters and my pipeline object P that I made, and it's going to use the 10-fold cross-validation, so the kind of the 10, it's going to run it 10 times for each setting to get the average accuracy. And I set n jobs to 1. You can set this to more to basically run a whole bunch in parallel. I think -1 makes it like spread out to like into some smart way of like as many CPUs as your laptop has. This may be like my own fear and intuition of using multiple threads in Python or something. I've had weird things happen with using multiple threads on this grid search, so I actually just keep it at 1 to avoid weird crashing. But that may be bad advice. But here we can run it. And you can see there's 18 candidates. It got that because it's 3 times 3 times 2 is 18 times 10 folds for each one of those candidates. So it's 180 fits that it has to run. So here it's done 1 job. Is anybody's laptop faster than mine? Yeah, awesome. What was the winner?
So with -1, it finishes in 17 seconds.
Oh, really? Huh. Yeah, I don't know. I got some weird errors that went away when I changed it to 1 when I was doing some practicing, but maybe -1's better. So you can see, so here basically what I'm going to do is I'm going to look for the best parameter. So it keeps track of the score for each of those settings. Yeah.
How does the grid search know which parameters are going to which part of the pipeline?
By this, so counts __. So I've named my pipeline step here,
Oh, I see.
and so then I'm attaching it here. Yeah, good question. Oh, there it goes. So it thinks that the best parameter here is, so it actually likes the the 50% max, so kind of removing the super common words, and then also removing the super rare words, and then using using n-gram, not the pairs of words. So this pipeline is super powerful. I didn't know if I had time to talk about building your own feature systems, but they're super easy, actually, right? So basically, if you overwrite fit and transform, basically now you have a feature selection class. And there's a thing that unions features together. So you can make a whole bunch of these yourself, and then also add those in. So I think if you wanted this to work effectively, you might want to check the number of exclamation points, right? And famously, there's some research on this. Like, you really want like emoji and emoticons, if you're doing sentiment, especially on Twitter. You also might want to include the length of the tweet, the language of the tweet. And you can actually make all these separate steps in your pipeline that it then combines into kind of one long pipeline. And so the fit is basically the part that's going to kind of set everything up. You don't need to, some things might not need that, right? But for the word counting, it kind of needs to know all the words. So it needs to kind of look at your set of data and say, okay, what are the words in here? But maybe the length of the tweet wouldn't require a setup, right? You're just going to do a length on the string that you get passed in. So the transform you have to overwrite to make something meaningful. And basically you're just passing around lists. That's all it is. But this kind of structure really helps you, because then if you want to include parameters, if you wonder, exactly like which emoji should I include, you can actually set up parameters for yourself that get passed into the constructor, and then in the grid search you can try a whole bunch of different things. If you put too much in the grid search, you might kind of overfit your data, right? So you might be, you might not, it may not work quite as well on a new set of data because you're kind of learning your parameters on your training data. But this is I think with this, actually, you should be able to take this and use machine learning for your real world examples. I hope. If you want more data to play with, we have lots of data sets that we have a free license for you to use. At crowdflower.com/data for everyone, we just publish tons of stuff. So there's lots of fun data sets if you want to play with them. Actually, if you do anything interesting with them, please let me know, because we want to use it. We want to hear about how they're used. Thanks for working with me. Thanks for having me. Feel free to email me, Lukas with a K at CrowdFlower, or tweet at me at Lukas with a K. Thanks, guys.